Alex.
Yeah.
Um, okay, so I hope all the participants are back in the meeting. So now we will be starting with our second session with Professor Gadgil. And I would like to call our very own teacher, Ms. Geeta Paluskar, to introduce the second speaker for the day. Over to you, Geeta.
Thank you, Alexander. Good noon to all the dignitaries and participants present on this forum. When I Google searched the name Dr. Siddharth Gadgil, I got abundance of references and links. And sir, it is indeed an honor, though also a challenge, to introduce you here in a few words. So I'll try. So, sir, as even during our informal talk just before this session began, explained that he completed his Bachelor of Statistics with honors from Indian Statistical Institute, Calcutta. After that, he received his MS and completed his doctorate in 1999 from California Institute of Technology. So though he started with a Bachelor of Statistics, he has completed his research work in the area of mathematics. I'll mention some honors and awards that he has received. He is a recipient of Sloan Dissertation Fellowship in Mathematics. He is an associate of the Indian Academy of Sciences, Indian National Science Academy Medal for Young Scientists. He received it in 2008. He is also a recipient of Platinum Jubilee Medal for Young Scientist, National Academy of Sciences, India. He has received NASI Scopus Young Scientist Award from Elsevier in 2010. Currently, he is working as a professor at the Indian Institute of Science, Bangalore. Prior to it, he has also worked as associate professor at the Indian Statistical Institute. He has been a part of several important committees like the UGC Review Committee for CMI, the UGC Advisory Committee for the Department of Mathematics, NEHU, Shillong. He has been co-organizer. I'm only mentioning a few, sir, because I'm asked to give a brief introduction. So he has been co-organizer of several conferences, the ICM Satellite Conference on Geometric Topology and Riemannian Geometry, the International Conference, Geometric Methods in Low-Dimensional Topology, IISc Bangalore, the conference, Low-Dimensional Manifolds and Groups, ISI Bangalore. His research interests are low-dimensional topology, including three-manifold topology and geometric topology of smooth four manifolds, geometric group theory in particular connection with and applications of topology, automated theorem proving and homotopy type theory. He has more than 40 research publications, including research papers and expository articles to his credit in various renowned national and international journals of importance. With a citation index of 409, I'm not sure, sir, whether it is the current figure. I've received it from one website. Please correct me if I'm wrong. And he also has several cross citations. Am I audible, Alexander?
Yes, yes.
He has guided 7 PhD students so far, and all of them are associated with prestigious institutions. Recently, his main focus of his work has been automated theorem proving. That is, I guess, trying to get computers to do mathematical proofs. The one success so far has been the Polymath 14 project, which resulted in the publication in the prestigious Journal of Automated Reasoning. Interested students, participants may Google search Polymath 14. You will also get to see his presentations. His work is available on ERNet, and I'm not very sure how to pronounce this, arxvi.org. I hope I'm right here. Sir, I'm sure our participants are eagerly waiting to hear you on the interesting topic of contemporary areas of research in mathematics. So over to you, sir.
Thank you very much. Thank you very much for the kind introduction. Yeah, so AR, that's actually ARchive. It's pronounced archive, if you want to know. So that's where it started in physics, since the question was there. I'll just start with say that it started in physics and then spread to maths and computer science. Most people put up preprints there. Okay, so it's the English word archive, but that Greek chi is written just like X. That's why it's capital X. Okay, so I hope I have shared that was just trivia. Yeah, so I hope I have, you can see my screen. I have a very rough set of slides here. Yeah, so unfortunately, not in person, it's not easy for you to interrupt me, but please feel free to put in the chat. I mean, those of you who are presenters can please feel free to interrupt me, and the rest put in the chat any questions that you want. And from the opening remarks and then some discussion before here, I gathered this is a wide ranging audience, including bachelor students and master students and some young faculty as well who are looking for research in mathematics. So the original slides I made were a little more high level. I will see, but they're not actually slides. So here you see this looks like a slide, but most of them are blank sheets of paper with maybe a heading with the open space to discuss things. And even though the topic is contemporary areas of research in mathematics, I first said some contemporary areas and then I made it a few contemporary areas. I think I should sort of emphasize research in mathematics today is extremely large. It's a vast field, and I'm certainly cannot talk about it all the contemporary areas or anywhere near. It will be a small sample. Yeah, so of areas. I mean, two reasons. One is that in 50 minutes, there's only this much one can say. But the bigger reason is that, of course, even if I'm given unlimited time, there are vast areas of mathematics where I know very little. So I did try to be a little systematic in the sense that I went and looked at the sections. So every 4 years, there is an International Congress of Mathematicians. I looked at the listed sections and so on to try to see that I haven't missed anything. And of course, scan mentally all my colleagues and see that I have included anything any one of them is doing or mathematicians I know elsewhere. So I'll speak about these things a bit. Okay, but to make things, so as I said, my original plan was a little more high level. I'll start with simply some general comments. Okay, so these are aimed especially at those who have not started their research and maybe especially at BSc or MSc students. I think first thing, yeah, so these are general comments about research in mathematics. And yes, this also partly addresses a couple of things that were in the chat earlier for the earlier talk. I gather you have a panel to successively highlight that. I think so. I learned that your college has one mathematician I know reasonably well, Rekha Santanam. So you have distinguished alumni. So those of you who are in bachelors here can feel that if they can do it, you can do it too. If you're comparable, I mean, if your fellow students can be successful. So research in mathematics is active. As I said, it's a large area. People in other fields, in fact, have a general sense that in mathematics isn't everything done. And unfortunately, it's very difficult to answer to the contrary because a lot of mathematics you quote really was done quite long ago. Okay, so I will try to give examples as I go there that to try to suggest that's not the case. There are many questions and there is much progress that's still going on. And how interesting it is, etc. You can judge and as it goes along. By the way, I heard the first speaker also, Professor Sani, gave some reading, but I would suggest you read a Mathematician's Apology if that wasn't mentioned. It's a nice dose for research in mathematics. This is G.H. Hardy's famous book, which is unfortunately way misquoted. Okay, but if you read it, also remember it was made in unusual circumstances. It was made at after a world war by a mathematician who was very traumatized by the war. I mean, people are, of course, traumatized by the war. So today we think of applications as largely making human life better because, well, we get this internet from the applications. I mean, hunger becomes rare and people are cured, people get vaccines. So when you talk about applications, From technology, you think of life being better. But at the time of war, it was a perspective of somebody who thinks of technology mostly as ways of killing people. Yeah. Oh, I'm sorry for this. Yeah. Okay. Sorry. So that was said. So no, there was a longer digression than I intended. It's active, but the more important point I wanted to make is that research in mathematics needs a lot of background. So let me be concrete. In the American system, for example, people do a bachelor's in 4 years, and then they take one more year in their PhD program learning mathematics before they start. So for most areas of mathematics, I'll focus on what is often called pure mathematics. Okay, but I'll talk about other things as well a little bit in passing, in particular just now. But in most mathematics, you need a lot of background. The reason is mathematics builds on other mathematics. When I get to details, I'll say this a little more. So if you're looking, occasionally an undergraduate does do some research of a serious nature, but these are really the geniuses. Of the undergrads I have taught, one, Sucharit Sarkar, actually did a significant piece of mathematics as an undergraduate, but then he went to Princeton for his PhD and had a major breakthrough 1 year after he got there. So what I'm saying is it's a very rare thing. It is not something that you should expect in the normal course of time. Okay, in certain applied areas, things may be different. In particular, if you see an area where a lot of undergrads are doing research, be a bit suspicious of it. It's not something that should happen. It means something is true. So concretely, as I said, and in Europe, for example, people will be ready for research after a master's, but that master's is a much more than the Indian master's. So you should imagine that you're not going to be starting research as undergraduates. It takes a lot of background, and you should be learning a lot, like core of it. Now it varies from field to field how much you have to learn as a background. So in combinatorics, maybe masters is enough, while in algebraic number theory, you might need many years beyond that. I'll talk about specific areas a lot. Okay, and the other thing is choose your, gather you'll get a lot of advice on your research topic, but here when I talk about areas, choose your area based one on what you like and what you're good at. Fortunately, there is enough self-selection, so it's unlikely that you will like an area that you're not good at. The two will often coincide, but also on on general principles, choose it wisely based on how active the area is. Okay, for instance, there is this book on for the first course in topology by Oleg Viro and others. It's called Elementary Topology Problem Textbook. And at the end of the introduction section, it says this subject is very attractive to students. You may want to work in it for your research. Don't. It's a mature subject. Most of the results are already done. Okay, so this is a warning. Subject might seem very attractive. I'll come to these in details. Choose your areas wisely. Yeah, so the other thing I'd like to say, because I'm mostly going to be talking about pure areas and not talk about details of any specific application. Yeah.
May I
Yes.
interrupt for a minute, sir?
Go ahead. Go ahead.
Sir, if you're changing your slides, I don't think I'm able to see
No,
the
I have not
change.
changed the slides. I have not
Okay.
yet got to my slides. Thanks for warning. So these are preliminaries on a piece of paper that I have just jotted down. Yeah, so these slides will have the more mathematical part. The other thing that I jotted down here is, of course, there are many applied areas of mathematics which are active. I will just say a couple of things if you wish to do that. One is you learn the application as well. Don't think that you can, for example, if you're doing mathematical biology, learn some biology. I mean, take a textbook and learn the basics. Okay, and also understand that people who are in that area, in particular experimentalists, are doing things that are difficult and skilled. Yeah, so I have, hopefully none of you have this problem, but general problem of mathematicians doing applications is extreme arrogance, a sense that they as mathematicians are a superior kind of human and they are bringing their mathematics to people fields which don't have any substance. No, you have to understand they're all non-trivial, the application domain, and learn it. So your knowledge should be the union, not the intersection of what the sub part of mathematics and what you're applying. Okay, so these were the general remarks. So I'm now on the wrong thing here. Okay, so I have just a few slides. As I said, most of them are blank. And as per the schedule, I guess I go on till 12:50. Yeah, so I'll go on till then. I'll say what I can. Let me get this thing. So this was the first slide. So I'll start with just an overview of what is research area in mathematics. Then I will discuss some of the areas, and then slowly I'll go into more and more detail. And then when the time is up, I will stop. Okay, so as I said, combination of my ignorance and finiteness of time means that I'm only going to be covering a sample. Okay, so this is really the more prepared part. Okay, so what do you mean by an area of mathematics? So I'd say it is determined by three questions. What are we studying? How do we study it? And why? Okay, the why is maybe within pure mathematics the least important to determine the area, but especially for applied areas, they're almost defined by what you're studying. Okay, not only applied areas, but especially applied areas while you're studying it for mathematical biology or communication theory, information theory, computing, whatever else it is. Okay, but what we study is what questions, what mathematical objects, and something related to this is when we consider objects the same. So I'm saying this now, but it will make more sense when I get to concrete examples, especially in geometry and so on. So a field is not just what we are studying, but how we look at it. And what we ignore, what we pay attention to, and all this can be made precise by definitions. How is central? So these are what you call what we would call techniques, to be studying things. Okay. And as I said, you also have why. Okay, so these techniques can come from another area of mathematics. They can come from so in natural sciences, often the technique is an actual instrument. And so progress often happens because you have a tunneling microscope, you have optogenetics where you can control single neurons in the brain, and so and so. This makes new research in a sense easier because a new instrument has now become available, and you can do things with it that you could not do previously. Of course, sitting in India, this is a bit of a double-edged sword because and especially if you're not in one of the handful of very well-funded Indian institutes, because maybe a new instrument is available, but you personally don't have access to it, then you're handicapped. So in mathematics, you don't have that disadvantage. But so techniques are just existing mathematical results, and they often come from connections with other areas. So typically, new discovery is a new discovery of connections with other areas of mathematics, and that will let you transfer understanding from one area to the other. Okay, so sometimes you have another breakthrough within an area, but very often it is a breakthrough which is using something in one thing to the other. Of course, there is internal progress as well. So you build upon understanding of previous people. And remember that cumulative understanding of people to this day is huge. So again, this is going back to what I said earlier. You need a lot of background to do research in mathematics. Okay, so I'll talk about different areas that are determined again by what we study, how we study, and why we study it, and what and how will be most of the things. So overall, what do we study in mathematics? Well, usually the starting point is something rooted in nature. It could be numbers, it could be geometry, which is rooted in spaces. It could be information also, so it could be things in technology as well. So you begin with something and then you abstract it. So abstraction means that you throw away, you ignore certain things and you focus on certain other things. There is a precise concept, there's no more than one, precise meaning to what you mean by abstraction. Even in programming, people talk about abstraction a lot. Abstraction can be viewed as either looking at extracting common features from different things, or it can be viewed as ignoring certain features and focusing on others. Now, all knowledge has abstraction at its core. As a simple example, when you're thinking of addition, well, the point is that whether you're adding 7 sheep, if you add 7 sheep and 5 sheep, you get 12 sheep. And if you add 7 stars and 5 stars, you get 12 stars. Okay, so it didn't matter what is it you're counting, it only the number mattered. So number itself is born of abstraction. And this is even true with physical fields. You don't study a particular glass of water when you're studying properties of water, what is common across all fields, but you can say mathematics is what you get when you abstract many, many levels. So you are no longer dealing with experiments, but with a fully defined system. Now, this is usually rooted in nature, but most mathematics going on today has gone through many processes of the things that I'm going to say, most importantly abstraction. And so it might be quite far removed from the empirical, from what we observe in real life. Now, one of the things that leads to new concepts and is connections between areas, thing to emphasize, and also common abstractions. You find that things to start with may look very different, but if you just look at specific aspects of them, ignoring the others, they become the same. This is very powerful. It not only lets you transfer study several things at once, it also lets you transfer concrete knowledge from one place to the other. So something which is concrete in one situation, you abstract it and then make it concrete somewhere else. I will mention specific things. This is one of the central ways of developing mathematics. So these are there. And the other thing that happens is that you start off studying a problem and then you have a technique and you treat that technique also as a problem, as an object towards study. Okay, so you'll already have seen this. You're studying the world, physical world. This will go back to Newton even. You study motion, concrete objects, and then you get equations of motions. Then you start studying equations. Okay, similarly, you're studying numbers. So you start with something which is a technique to solve a problem, and then you treat that technique itself, if it's serious enough, or the objects involved in that technique, as objects in their own right, interesting in their own right. And between these things of making techniques as real and abstraction and connections, mathematics evolves into this edifice. I mean, a very large building. It's not, I shouldn't say it's a building because it's not as it's going straight up. It's a huge network of connections and so on. Okay. So the quote above is Manin, by the way. Manin is an algebraic geometer. He has an article which is out here, but I won't switch it. You search by him and he has an article called Mathematical Knowledge, Cultural, Social, something aspects. If you're interested in this kind of general thing, you can read it. He's also a person, he has also written a beautiful book on logic. So if you have many people are interested, which is aimed not for logic itself, but for people in mathematics who want to understand logic. Okay, so now something concrete. So as I said, many areas are determined by what they study. Okay, so numbers, of course, you study in number theory. Space, we live in that. We as primates have a very large visual cortex, and that is something which we hence plays a major role in our real life. And this gets abstracted into various branches of geometry, topology, algebraic geometry. I'll say some things in detail as we go along. Yeah. Chance, randomness, so probability and statistics are rooted in that. The study of change is dynamics. Of course, there's a lot of, as an example, these two both intersect in what we might call stochastic processes or something like that. That's just one example. Okay, and then these are concrete things that happen in the world, but you have notions of the world like symmetry, which plays a very major role in the world itself. Laws are symmetric, but in mathematics. So group theory was born out of symmetries, and Lie theory, as it's called, Lie groups, Lie algebras, and representation theory. These are all born from understanding symmetry. And then you can go to one level further and try to understand mathematical reasoning itself, the process of reasoning. That is the subject logic, set theory, category theory. Now, within mathematics, logic was a very active field in the early 1900s, first half of 1900s, ranging from axioms of set theory, but predicate calculus. So that was before. So from maybe 1850 to 1950 or something like that. It was a very active field, and so then it matured, in a sense, the work of people like Church and Gödel. Everyone here, many of you would have heard of Gödel's incompleteness theorem and Alan Turing and so on. But then it moved to computer science, remained active there. It continues here. Continues in mathematics. Set theory is fairly mature. Category theory is a higher level of abstraction which has developed. Nowadays, higher categories are again reasonably active. And then we study finite or more generally discrete structures and combinatorics. I won't say much about combinatorics. In fact, I'll say almost nothing about it. So just so that it exists. It is also a fairly active field. It's becoming important, partly growing in importance, partly because of its connection with computer science. Okay, but on the other hand, some areas are really defined not by what, but how we study them. Okay, so I said what and why. That's a mistake. What and how, but especially how we study them. So again, you can look on the internet. There is a famous case about chewing corn. So basically, the techniques of analysis of mathematics fall into two big classes. One is algebra, which is studying structure and regularity. And the other is analysis, which has to do more with bounds, estimates, specific arguments, and so on. So everybody is at heart almost an algebraist or an analyst, you would say, and every field has any particular style of working tends to be rooted in either algebra or analysis. So there is, you might find on the internet so a particular mathematician wrote this, or maybe it was a computer scientist, I forget exactly which, that when you're chewing corn, that is a bhutta, there are two ways in which you can chew it. And he found that half the people chew it one way, another half chew it the other way. And this is correlated with whether you're an algebraist or an analyst. It is also correlated with which kind of programming language you like and many other things. Okay, so there is a fundamentally techniques are either studying structures or studying things with bounds and estimates. Yeah, so I am purely an algebraist, and this will bias what I say throughout this. I will tend to, except for the geometric side. So my source, I do not do number theory. My source is always geometry biased. I'm geometry and algebra biased, and so that's just a warning that my representations of different areas is not at all balanced. So everybody's isn't, but this is the bias I bring. So partial, but on the other hand, people do study analysis and algebra in its own right. Okay, this is a case of techniques becoming the objects of study. Okay. In addition to this, as I said, many areas may also be derived from study of nature and so on, more directly. Ultimately, everything is probably, but okay. So now again, some general comments, and then I will start talking about specific areas. So what makes an area active? As I said, areas may or may not be active. So there should be interesting questions, and interesting is a bit subjective. Some people find something interesting. Some people find it very ugly. So I won't get into what causes things to be interesting, but they should at least be not trivial. They should not be easy. So if every result is easy and really not easy to anybody, so there should be questions that are non-trivial. That's a minimum criterion for an area of mathematics being interesting. So having interesting questions, but also you should have progress being made and on the interesting non-trivial questions. Yeah. So okay, at the end I will come to that. Now these are necessary. If you don't have such things, usually, now sometimes it can happen that an area is very active purely internally. Okay, so that is to say that you have interesting questions, and there could be a decade or two where some area like three-manifold topology, maybe just building on itself. More and more interesting work is being done on finite simple groups. People are just working within the area, but they are making a lot of progress on interesting non-trivial questions. But more commonly, areas become active if there are no new techniques. So when you choose an area to work on, or when you're working on an area, ask why is it that you could not do some, I mean, you're working on a question, why has it not been answered before? If you think it's because you are smarter than everyone else. You're almost certainly wrong. Okay, with probability 1, you're wrong. Well, certainly I would be wrong if I said that. And there might be one person of the 56 here for whom it may occasionally be true, but that's rare. It is almost inevitably because some new technique has come. Okay, you are managing to use some new insight, some new technique in the field. So it's not been done before because either the why is new or the how is new. So there are so either you have new techniques or some application has made a field suddenly more interesting, and so the question was not addressed before. Okay, and so that brings the fourth point. So the area is active if it answers questions in other areas. Again, this is not compulsory, but it's very important thing. So it's either, but okay, I mean, any field of mathematics, you can say answers some questions. But if 100-year-old progress in number theory answered questions in cryptography today, that does not make number theory itself active. By the way, number theory is active. I'm just saying the thing is that either the results are going to be applied in a new way, or better still, new results in a field are being applied in another field, maybe within mathematics. Okay, and again to emphasize, so areas can stagnate. They can stagnate in various ways, and I'll give a concrete example here, which may not be understandable to many, but still I'll try to be specific. I'll still for concreteness, so they can stagnate in various ways. You can have very interesting problems, but little progress. This is the sort of dangerous thing because it looks very tempting. One of the examples I'll give is a very fascinating question in geometry. Okay, it's a field which doesn't have a name for this reason, I suppose, is whether S6 has what is called a complex structure. Which spheres have complex structures of yours? It's a very basic question. And the reason it's basic is it looks like an isolated question, but it's really a typical example of a vast school of interesting questions. Now, this question has been very interesting and studied since the 1960s, at least, and nobody has made any progress on it. So you can have very interesting questions and you can say, look, there are such interesting questions, so this field must be interesting. But if nobody actually makes progress on those interesting questions, okay, then the area is not active. And so you could also have this odd situation where you have lot of trivial, boring things where people are rapidly making progress, and some very attractive questions where people are making no progress. That doesn't compensate. These don't average. The other thing is if your techniques are old, you typically have diminishing returns. Okay, this happens with an old style of algebraic differential topology, which people still work on. But once you're using ideas that have been around since, say, the 1960s or 70s or something like that, 30, 40 years later, sometimes you have dramatic progress. Sometimes old ideas lead to dramatic progress, but this is very rare and you should not bank on it. Typically, if you're not using newer techniques, then it is likely that anything interesting somebody else has done. Okay, so other things that can happen is increasing isolation from the rest of mathematics. Your results become more and more internal. This happens, for example, in finite simple groups, people say that. So finite simple groups had a very major problem. Finite group theory had a very major question. And till that was answered, the classification of finite simple groups, it was a very central area in mathematics. Now, people in the field will keep saying that there are still plenty of interesting questions, and it's true. And there is progress being made. But then when that progress is no longer considered important for the rest of mathematics, the area starts getting diminishing importance. Okay, so these were generalities. Let me sort of start with a few remarks about various specific areas. So as I said, things are defined by. So symmetry led to group theory. Okay, so group theory was really invented by Galois in the old form. Modern form of group theory is largely the work of Emmy Noether in the earlier 20th century. But group theory in the broad sense was born by Galois, who was studying the symmetries of groups, of solutions of an equation. Okay, so the roots of an equation have a certain symmetry, and using that, Galois was able to answer a very basic question about which equations can be solved in terms of radicals, roots, and which can't. So it was already known that you could, I mean, all of you know you can solve a quadratic equation. Some of you may know you can do it for cubics and even quartics, degree 4, but degree 5 you can't. Abel had shown that. But a systematic question of what can be solved and what cannot depended on understanding of symmetry and how that gave you an insight into solvability. So that was Galois theory. Okay, so this led to groups, and then Cayley showed that very abstract conditions tell you what makes groups a group of symmetries. So that so group theory is typically finite symmetries, what is called group theory, and especially roots of equations was the root. But in the late 1800s, sort of independently, you had continuous families of symmetries like translations and rotations were being studied by people like Lee and Klein and Poincaré. This is the theory of Lie groups, as it's called. It is so Lie groups. The basics of Lie groups are known by the work of Cartan around the turn of that last century, that is around 1900 or early 1900s. Elie Cartan. So there is a Cartan-Klein classification and so on. So that's but there is a lot about Lie groups which are still active. So now what happened is that if a group is not continuous but it's infinite, okay, this was a sort of orphan subject. Geometric and topological methods have made it alive in some sense. Also arithmetic methods, number theoretic methods. So these are still a lot less is known about them. There are many active questions here. I'll briefly mention it about. Now you can flip it around. You can start with an abstract object and ask how it acts by symmetries. This is a field called representation theory, the basics of which are old, but arithmetical aspects as well as things to do with infinite dimensions and so on, which are connected with harmonic analysis, is a very active area. In particular, it's very active in India. A lot of people are doing representation theory. Little more, I mean, not the very core questions, which was work of Frobenius and Schur and Lee and so on, Cartan, long ago, about a century ago, but a lot of representation theory is quite active. So the thing is that by studying concrete behavior of groups, you also understand the structure of groups and Lie groups. So there's an interplay between these fields. So okay, numbers, these are even more basic. So what are basic questions about numbers? So here I'll give a little more of an example. Okay, so basic question about numbers, two I would say. Okay, so let me write an example of the second, which I believe everyone would have heard of. Fermat's last theorem is a question about whether x to the n plus y to the n and z to the n. Okay, and of course for NS2 these are Pythagorean triples. 3 also there are examples, I think. I think it's 4 and above, or is it 5 and above? I forget. The Fermat's last theorem, as it was called, and proved by Andrew Wiles and then Wiles and Taylor, is asking whether this has integer solutions. Okay, but even if I fix up a specific n, 1000 or something like that, okay, it's not at all obvious whether it has integer solutions or not. Okay, and this is a basic question in number theory. So the question is when you're looking for solutions of equations, but that are integers, that are rationals, and so on. Okay, so I'll come, and the other question is prime numbers. So basic result in mathematics is there are infinitely many primes. Okay, but you can refine this and say that there are infinitely many primes even in an arithmetic progression. This is a theorem of Dirichlet. I'll come to that in a moment. Okay, but before that, I'm going back and forth a little bit between these two. Let me just say this. So I'll, yeah, so I'm just opening the chat. Okay, yeah, so the basic question. So let me come back to this. So these are what are called Diophantine equations, and there is a major result proved in the late 1950s. It is the culmination of a whole work of a whole lot of people, from Church and Turing and Gödel through Hilary Putnam and Julia Robinson through to Matysiewicz, I think is the one who put the final things, saying that there is no algorithm That is, that you cannot write a computer program which will take as input a Diophantine equation like this, meaning algebraic equation, and tell you whether or not it has integer solutions. So this is unsolvable. This tells you that number theory specifically is endless. In general mathematics is endless. Okay, so that's why you cannot. So you have an endless sequence of ways of solving it. Okay, so let me first, since I started talking about the second one, say more about this. So one way in which you can solve this in part is ask if there are real solutions. If there are no real numbers that are solutions, of course there are no integers, and finding whether they're real solutions or not is a lot easier. Okay, but then it was realized that you can also look at this equation and ask, for example, I won't go into details. For example, sometimes you can say there aren't solutions by looking at odd or even, or more generally by looking at remainder when you divide by some prime. And you can do this in a sequence, what are called p-adic solutions. Okay, so that's one of the basic techniques in number theory. It leads to algebraic number theory, which is an active thing. And in particular, very important questions are refining this. It's not, instead of just asking whether you have a solution or not, you can ask how many solutions, and how many may not be a number, but what are called a rank. And indeed, you may have heard there are millennium prize problems. So one of them is about the rank of the number of solutions to this. It's Birch and a conjecture of Birch and Swinnerton Dyer, which connects this to something else of an analytical nature. Okay, so far this was these are some questions to talk about. So for fairly simple equations, cubic equations, what are called elliptic curves, understanding how many solutions they are is an active area, and it's quite non-trivial, in fact, bound to be, but it's one where it's a rich area. So let me turn a bit to the top thing. So here in the top, so there are infinitely many primes. There are infinitely many in the arithmetic progression. This is a theorem of Dirichlet. So prime number theorem tells you the density of primes. This was Erdash and Selberg. This was a while ago. But here are two new things. So twin primes is the strong question. So if I look at 3 and 5, they are primes next to each other, 11 and 13, 17 and 19. These are called twin primes. Now, are there infinitely many or are there finitely many? We still don't know. So this is a question. So is it all done? It's not. But then I warned you, there may be a danger that there's an interesting question but no answers. But indeed, you can weaken this and ask that if I fix the difference between two primes, that is, I'm looking at P and P plus D, I'm allowing D to be anything but fixed. Are there infinitely many such pairs which are a fixed distance apart? So Yitang Zhang proved this 4 or 5 years ago. So this is recent progress. It's a dramatic story, but I won't go into this right now. So here again is an interesting thing. I'll come to it in this. So you have arithmetic progressions. So the whole arithmetic progression cannot all consist of primes. So basic question is, can you have for any k a sequence p, p plus d, etc., p plus k minus 1d? Can you have a length k arithmetic progression which so that all of these are primes? And this was proved by Terry Tao and Ben Green around maybe 2004 or so. So again, recent things. Oh, I think I went the wrong way. So the principle here, I don't want to go into this in too much detail. So Terry Tao has talks and in fact articles on this. And this goes back to at least Furstenberg's work in the 60s. So the idea is that okay, since I don't have much, I've taken a long time with the basics. I won't say this much. So there is an interesting point of view here, and this comes into ergodic theory and so on, which are areas that are applied to number theory. Idea is that primes are clearly not random. Okay, they have some structure. For example, almost all of them are odd. Okay, but a point of view that Terry Tao, Ben Green took and so on, which is useful, is to try to say that there is some algebraic structure and the rest is random. And the rest is random in a very specific sense. By random, this doesn't mean you don't understand it. It means you satisfy certain probabilistic laws. Okay, and a view that is that lots of questions can be answered if you can say some things have structure and you understand them algebraically, and the rest you understand probabilistically and analytically by using such a dichotomy. Okay, I won't write anything on this slide. So which gets to the next active area. Probability, I won't say much about it, but this was within Western, including traditional Indian mathematics, quite neglected, though in Russia it has been strong. But recently it has become very central to mathematics. It has become, it is very important. It's a very fast growing area. In applications, it's always been important, but even there it has grown a lot. Okay, so let me just say something about this. So I just use the word random. Okay, so we can study. So let me take a physical example to emphasize this. So we can study, of course, solids or crystals in the real world. And these are studied using order. Order, symmetry, groups, algebraic structure comes in. Okay, so this is, of course, obvious. But what Boltzmann discovered is that you can also study gases. Okay, and here you do it by using randomness in a useful way. So the thing about a gas is you can study it because its behavior has a certain regularity, but the regularity comes from randomness, not from uh, uh, because of things averaging out. Okay, so what happens is things average out and you have very specific results like law of large numbers and central limit theorem, which tell you that random things behave well. Central limit theorem. And more such things are known. And this has made this quite a useful way. And so what you can understand is some sense what happens is gases mix a lot. So this the concept is called ergodicity or mixing. This has been useful in areas from topology to number theory and many applications, also elsewhere outside mathematics. Okay, and the other thing that happened, I will skip this unless there are questions. But so I won't skip it. I'll say very little about it. So we have different phases of matter. So similarly, many mathematical systems have phases, and they can be studied sometimes using order, sometimes using averaging. And the most interesting things behavior is during phase transition in many cases when you switch from one phase to the other. And this can be studied using what is called conformal invariance. And so a new technique that was created by Oded Schramm, who incidentally is a topologist. He actually happens to be a mathematical uncle of mine, I believe. So same mathematical family as me. He started off as a topologist, Schramm, but he revolutionized the field by showing how complex analysis plays a major role in topology. This is very active. It's very active in India as well. My colleague Manjunath is one of the people who does this kind of thing. Not just this, random matrices and so on. So probability has become active also because of new techniques, in particular complex analysis in probability. Okay, geometry I can talk about a lot, and so let me, so I had 2 slides for that, but I will just use one. So geometry, you would already see at a basic level, there are 2 things you can break into. So there is what is called analytical or coordinate, and the older style, which is synthetic. Okay, there are other ways in which you break things. So when you're studying geometry, you may study very symmetric objects, which leads to the symmetry related fields that I talked about. Okay, but they all get mixed with each other. All these aspects get mixed up with each other. So how much symmetry? Are you studying really symmetric objects or arbitrary objects? Okay, and the big division here is between algebraic geometry and what is usually called geometry/topology. Yeah. So algebraic geometry is where you study things given by equations in terms of the equations. You're really studying the algebraic structure. This connects with number theory because, as I said, a basic question in number theory is solutions of equations. You can take geometric ideas from there and transfer those to number theory. Okay. And geometry and topology itself breaks up into things like differential geometry, which studies curvature. and topology, which is essentially the study of global properties. Okay. So I've adjusted the level. I was going to go into more details here, but I will only according to questions. Okay, so I won't say more about. Topology itself has many branches. There is what would be called set topology. There is algebraic topology, which, as I said, is largely a mature field. Pure algebraic topology does have some recent progress of a significant nature, but it does tend to be very technical. Geometric topology is much more active in recent times, and especially its connection with other fields. Okay, so topology itself breaks into things. I won't go into details. I won't talk about geometric topology in any greater detail. And what has become very important, so differential geometry, the central aspect is curvature. And the easy way of thinking of it to start with, if you haven't seen it, is a straight line is given by f double prime equals 0. So in general, curvature is the second derivative. Of course, this is the simplest form of curvature, but in general, various notions of curvature can be captured with calculus. Okay, and closely related, you can study equations on a curved space. That is what would be called geometric analysis. This, I have to mention, is a booming field in a sense. It's you have the, including with applications to topology, you have what's called the Ricci flow, which is an important technique, and so on. So this is a very active field where geometry mixes with analysis, which is based on differential geometry. Algebraic geometry, as I said, is where you're studying spaces given by algebraic equations. Again, another active field, and particularly one of the strong fields in India. It's maybe the strongest field, especially in TIFR traditionally. So algebraic geometry. Now the algebraic aspects of algebraic geometry are what are called commutative algebra. Okay, algebraic sides. So and this is a very interesting thing. Sorry about that. So I'll just say a bit more about this. So complex geometry, and specifically what are called Kähler manifolds. This is very active. I can just give as an ad. If you want to work in it, you should come to IISc. Ved, Vamsi, and so on are the best people in this business. But the interesting thing, of course, you can work with Indranil in TIFR, for example. The thing about complex geometry is this is the intersection of differential geometry and algebraic geometry, and what would be called several complex variables, so complex analysis. So all of these things come together, as well as some really dramatic new techniques due to Gromov from the 1980s, forming a field called symplectic geometry, or rather symplectic geometry is older, symplectic topology comes in here. So there is this field which is born from the interaction of many areas called complex geometry, which is very active. And on the other hand, another active and interesting area is the application of geometric and originally topological ideas to groups, and also more generally to data. So the topological data analysis is an applied field related to this. Metric geometry is the study of curvature without using calculus in, for example, discrete spaces. So I've gone through. Oh, I thought I had some slides on different sides of number theory. I seem to have lost those, which is fine since I should stop now. Let me just say there are many other areas I mentioned in passing. Set theory, logic, combinatorics, dynamics, PDEs, analysis itself, people who are primary analysts, or algebra, various applied areas, and a new area is computer proofs in mathematics. So I'll say a couple of sentences about this. There are two aspects to this. One is the discovery of proofs that has not been so successful, and the second is verification of proofs. And this is a young and booming area. It's grown enormously. And the other fields, when I said enormously, they were on decadal scales, but over maybe the last 2 years and so on. So it's a field that is growing on the scale of years as we speak. And they are closely connected because writing a full proof in a way that a computer will understand is difficult. So the computer should fill in details. So automation and formalization are very closely related. These also have very practical applications in hardware and software and so on. Okay, so this was really a rapid, almost listing of fields and saying a bit of what they are. and some general comments about what fields are. I hope this was slightly useful, and I'm happy to take any questions. I will just stop from my side now. Thank you.
I think someone has raised the hand. Shivek, you want to ask something? You can unmute yourself and ask. Anup, please allow him to ask.
Yes, enabling the mic. Yeah,
Yeah.
it's done.
Yes, sir. Thank you for the session today. It was a very knowledgeable session.
Thanks.
I have one question regarding this stagnated areas.
Yeah.
So, Riemann hypothesis is one of the most celebrated problems, and
Right.
as we can see, complex analysis has not many tools, quite a few tools, but not as many as different analysis areas. And
Okay.
the and the last progress made in this problem was by John Nash some 2 decades ago. So
Okay.
can we say that Riemann hypothesis is actually a stagnated area?
So this is actually a okay. Okay, I should, like a politician, say yes and no, but I don't want to say that. No, so it's actually a very important question that you have raised. Okay, so in one sense, yes, if you mean to say, should you work on the Riemann hypothesis? If there has been no progress in technique, no new technique, and no progress for a long time, you probably should not work on the Riemann hypothesis. Okay, so if you want to say this, yes, then yeah. So when you talk about areas being stagnated, yeah. So let me collect my thoughts and answer this. It's an important question, and it's a very good example to say. Okay, so when you talk about areas, it's a nest, right? You have broad areas, you have sub areas, you have even smaller areas, even smaller areas, and then you have problems within that area. Okay, so Riemann hypothesis, for example, is an example of a specific problem, and the stagnation and no progress on this suggests that you should not be working on the Riemann hypothesis. Okay, question is, how much higher should you go in terms of the area? Now, analytical number theory, the study of, so I've lost that slide bizarrely. Was there a slide with the Riemann zeta function somewhere? Ah, yes. So here was the technique. So the Riemann zeta function was born in this formula. Zeta function is related to the distribution of primes. Okay, and broadly analytical number theory, Dirichlet's result used a variation of these, what are called L functions, and analytical number theory, which studies L functions and other such things, relatives of the zeta function, with different kinds of symmetries. Okay, so which studies different kinds of the more general, this part of analytical number theory, what is called modular forms, and more generally automorphic forms, is a very active area. However, if you're talking about purely using complex analysis, so that is not just complex analysis, that is complex analysis together with symmetries and symmetries of an integer nature. So that's a very important, so automorphic forms, modular forms is without a doubt a very active area of mathematics. However, if you are talking about it in a more, so yes, certainly you can work in analytical number theory in today it's an active area if you're working on modular forms, automorphic forms. However, I should clarify, because this is why your question is important, because there are different dimensions. There are still people who are working using pure complex analysis on Riemann hypothesis like problems. And as you said, the moral is don't. If all you're using is basic complex analysis, automorphic forms uses a lot of other things, representation theory, for example, and so on. If what you're working is old-fashioned Ramanujan style using complex analysis to prove Riemann hypothesis, not necessarily the Riemann hypothesis, but this kind of analytical number theory, then that should be regarded as stagnant. Yes. So in topology, sorry to go on. In topology, I'll just say one more thing. Somebody had written, there is a people would say many topologists would get this disease called Poincaritis. That is, they would spend 20 years trying to prove the Poincare conjecture and stagnate otherwise. So getting stuck on a hard problem can be a problem. Yeah, that's all about this. Thanks.
Thank you, sir.
Yeah.
Anyone else wants to ask the question? Sir, I think there are 2 questions in the chat. Possibly
Yeah,
you can.
let me see them. Yeah.
Tushar.
So foundation or proof theory. This is actually okay. Let me. Okay, so and then there are to do with game and chaos theory branches in India. Okay, so let me answer the second, which is somewhat easier to answer. Game theory, there are people who work on, but there are people in economics or computer science. Okay, I mean, there is Professor Narhari in computer science here who works on it and so on. So this is applied game theory. They have these. They keep calling it bandits problem, which annoys me because why should they expect we understand what they mean? Bandit is a lottery machine. So, but since this is within mathematics, no. Chaos theory, I'm generally suspicious when people talk of doing chaos theory. The proper term is dynamics. Dynamics is active. It is active in India in so Indian mathematics community is in general small in most areas. So active may mean that there are a handful of people who are doing very good work. But in dynamics, there are people who are working in complex dynamics. Well, and there are some in TIFR. There is a very rich school. This is Professor Dani and his students and their whole school of ergodic theory in India, which is closely related to that with applications in number theory. That has a whole range of first-rate mathematicians. It ties up with this discrete subgroup of Lie groups, which is another field where Indian mathematicians have done fantastic stuff. So dynamics, yes, is active in India. Foundations and proof theory, again, it's coming into mathematics through these computer proofs, as I said, and what was called homotopy type theory. So foundations or proofs more or less became peripheral within mathematics, but quite alive in some areas of computer science, in particular for programming languages and so on. So there is a Indian Logic Association. They have people. So it is. So here there is in CS Deepak D'Souza. There are people in IMSC and CMI in Chennai. Yes, that's there, but within mathematics, it is only now coming back in the form of computer proofs. In the longer run, it is for a while it was really what I said with internal. It became a corner of mathematics, not connected with anything else, because the progress became more and more internal and esoteric questions. That's still a danger with this area. If you're looking at foundations and logic not from their connections with applications, programming languages, or nowadays computer proofs, but internal questions, they became more and more intricate and less important to the rest of mathematics beyond a certain point. I mean, exact details of which axioms are relevant to what is not that central. And so, yeah.
I think there are no more questions. Anyone wants to ask? Please unmute yourself and ask.
Someone's raised a hand.
Someone has raised their hand. Yeah, please.
Yes, sir. Again, Riemann hypothesis related question. Sorry about
Okay,
that.
no problem. Yeah.
I wanted to know that you suggested not to work on Riemann hypothesis since it's a stagnated area where no progress has been made. Riemann,
Right.
I can classify Riemann hypothesis as a very big area as many people are working on it. But what if I want to work on it? What can be the certain time when I can start working on it?
Okay, so let me tell you a parallel story. Andrew Wiles, as you may know, proved Fermat's theorem. That's again a famous problem in mathematics. He dreamed of solving this as a child. Okay. And then when he became a respectable mathematician, he stopped working on it because it was not reasonable. Now he returned to working on Fermat's last theorem when Serre, whom most of you would have heard, many of you would have heard of, Serre is a leading mathematician of the 20th century. He started off as a topologist, got a Fields Medal for that. He's that good, and everyone knows him as a number theorist. So he's a good enough mathematician to get a Fields Medal for his minor subject. So Sayre showed that what is called the Shimura-Taniyama conjecture, which has to do with automorphic forms, implies Fermat's theorem. So Andrew Wiles was already working on the. So what happened is that the Fermat's theorem became a special case of what is a special case of a very important result of a whole field. Okay, so Riemann hypothesis is not a field. Fermat's theorem became a special case of a big field, algebraic number theory, and then Wiles worked on it for 7 years. And he didn't just prove Fermat's theorem, he proved the Taniyama-Shimura conjecture, which implied Fermat's theorem. Okay, so this is one example. So I'm giving you examples of people who successfully proved problems. The other example, which I know much more about, closer to my field, Grisha Perelman, who famously in isolation proved the Poincaré conjecture in topology, in fact geometrization. Again, you should realize, so Grisha Perelman in the late 90s, before he disappeared and worked on his own for 5 years or so producing that proof, had observed that the proof of geometrization involves two areas coming together. So you have to understand something which, so there was a field, so things made a whole series of progress called, starting with Ricci flow as it was called, with Hamilton's. So there was steady progress. And then at that point, you needed two areas and you needed progress in both areas. Now Perelman is a very remarkable person that he was able to make progress in both areas and hence prove geometrization. But remember, you should realize that in one of the two areas, which was what are called Alexandrov spaces, before he started working, he was already the best expert in the world. So Perelman's thesis was the most important work in one area. He managed to make progress in the other and come together. Okay, so the short answer is don't work on the Riemann hypothesis unless and until it comes from you have an approach for it. It involves one or more areas of mathematics and you have already proved hard theorems in that area. So if you have a pathway to the Riemann hypothesis and that pathway involves doing top level mathematics in an existing area and that pathway will take you to the Riemann hypothesis, you get to it. That's fine. Okay. But nobody, I mean, any example you think of in modern mathematics. So in topology, again, you had a serendipitous breakthrough in the 1980s. Simon Donaldson, he worked, he suddenly found some argument which led to a major field of topology. He created the field, but again, I should emphasize, he not only was he a genius, he was working with Atiyah and Bott and so on, who were the leaders in the field which got applied in topology. So this was an unexpected connection from another field, but he was already, of course, you can't say a leader. He was still a young research student, but he was already an expert and part of a group which was the leading group in another area. Okay, so when you're working on a problem, this is the general advice. Never expect, not even Grisha Perelman could prove the geometrization by being smarter than everyone else. Of course, he was smarter than everyone else, but he's proving the geometrization involved two things, one of which was just genius, but the other half of it was where he was already the world expert before he started working on it. So if you have a pathway to the Riemann hypothesis, which has three pieces, and you can show that you are the world expert in two of those, then you can try the third and go for it. If you're not a world expert in anything, don't try to prove the Riemann hypothesis. It will be a waste of time.
Thank you, sir. That answers
Yeah.
my
Yeah.
Thank you, sir. There is one more question in the chat.
Yeah.
There are two, but
Okay.
at least you answer about the quantum calculus. He has asked Vijay Singh.
Please tell about quantum calculus. I'm sorry, I don't understand what you mean by quantum calculus. So, well, there is what is called quantum field theories, quantum algebras, and so on. Yes, so there are many areas of mathematics, most notably functional analysis. And do you mean quantum computing by some chance? Well, anyway, functional analysis, but topological field theory, quantum field theories, and so on. which are rooted in quantum mechanics. They are often active areas of mathematics, including what's called non-commutative geometry. They are active in India. So Rajaram Bhatt at ISI for Bangalore, for example, works on them, and more senior Kalyan Sinha. And there are many people who work in these areas. TQFT is fewer, but there are people who work in these areas. So I don't know what you want me to say or much I can say about this. Okay, so the other is a more mechanical question. I will answer this. You may also want to ask about mechanisms, but I think since you have a panel dedicated to them, ask them also. Is one capable or qualified to do research work in math if he has not been in creamed institutes in his bachelor's or master's? Okay, so easier question is with bachelor's. Fortunately, the quality of master's programs, which was already pretty good, but over the years has got higher and higher in many of our IITs. So I know many mathematicians who did a bachelor's in their local college and then masters in IIT Kanpur, Madras, Mumbai. Of course, Mumbai is maybe the number one in this, who have then done very good mathematics. There are also people who have I can point out, who have gone to integrated PhD programs and they have done it. Let me track. So one of my colleagues, Venkatesh, for example, his bachelor's and master's has not been in any premium institute because he's from a small town in Tamil Nadu. Similarly, one of my former colleagues, she had to move for personal reasons. Pooja Singla, she is also did these. So the Venkatesh did his PhD at TIFR and Pooja at IMSC. They are both successful mathematicians today. It is harder. Okay, so you have to get into a PhD program in one of the. You have to have a good PhD program. There is really, I don't know of any case of somebody who's really a successful mathematician who hasn't gone to a decent PhD program. Of course, there are people like even in my field, Mladen Bestuina, for instance, who's did his PhD in Louisiana State University, which is, I think, or some such, which is not a top university, but he's absolutely at the top. So people can go from a medium PhD onwards. But but again, you have to. But yes, there are many examples. It is harder and harder the later you go to a top institute. But as I said, I have colleagues who are very much successful mathematicians who have done their bachelor's and master's in local colleges or universities. So no, it doesn't rule it out. But at the PhD stage, you really have to try to get to a serious research institute. It's very difficult without that.
I think now questions are over. Looks like. So anyway, if you have more questions, you can always put it in our group and we can pass them on to the sir. Okay, I think that will be better. So now I'm closing this question answer session. There will be a break. So after I propose vote of thanks, you may leave and our next section will begin at 2 o'clock. So